So today we're gonna introduce a new topic, Simplex method sensitivity analysis. Suppose you have a linear programming maximization problem where the objective function is maximization for c1 by x1 plus c2 by x2 plus etc. subject to a linear constraint which we formed in a standard form. So to know how this sensitivity analysis work out, we should define some operational definitions. So all our variables, including our decision variable and slack and surplus and artificial variable, are within matrix X. The basic solution are denoted by X of V, so it can be a decision variable or a slack or surplus depending on your solution, and also the non-basic solution are denoted by NXV. The profit or the cost are denoted in C, whereas the basic solution have CV and the non-basic solution have NCV. The technological coefficient are found in matrix A, so they are the coefficient for your constraint. For slack and surplus and the artificial variable, the coefficient is always 1. The coefficient for the basic solution is denoted by matrix B, and the coefficient for non-basic solution are denoted by matrix NAV. So the right hand side is within array B, so regardless the problem was more or equal or less or equal. So generally we will when we have a constraint, they are denoted by less or equal. If you have a constraint more or equal, you just reformulate it by multiplying both sides by a negative value, so the problem becoming less or equal. So for example, we have this constraint x1 plus 2x2 less or equal to 5. The other constraint was 3x1 plus 2x2 more or equal to 6. So when you put the first constraint in a standard form, it will be becoming x1 plus 2x2 plus x3 equals to 5. The second constraint, you should multiply both sides by a negative value, so it becoming minus 3x1 minus 2x2 less or equal minus 6. Then you can have the standard form for it, so it becoming minus 3x1 minus 2x2 plus x3, which is equals to minus 6. This notation is very important because we're gonna use MATLAB for the sensitivity analysis. So in general, when you have a maximization problem, so it will be denoted as follows: maximization of Z equals to the array C multiplied by matrix X. So these are the decision variable. For the slack and surplus, it will be continuous with zero coefficient. subject to, so you have the matrix A multiply by the matrix X, which is equal to the array B, where all your decision variables and stake and surplus variable are in the economic quartile, so all the values are more or equal to 0. So this is the form in any iteration. So like while you're solving your problem, so this is the formula for your tableau. So let's take a look for it. So over here for this body, we have the coefficient for the non-basic solution. So this is the B inverse, which is the coefficient for the constraints for the basic solution, multiply by AJ. So if this quartile is representing only the non-basic solution, so AJ here will be NBV. If you still in the first iteration or you don't know what are the basic solution or non-basic solution, so you're gonna extend this matrix to cover also the identity matrix. So basically the identity matrix having the same equation here, but we luckily because we have the basic solution, so it will be B inverse multiplied by B, so it will be equal to the identity. Of course, because these are the basic solution, so Zj for this one is equal to 0. For every non-basic solution, so the answer will be Cv by B inverse by NAV minus NCV. The answer should be as array. Here we have a 0 arrays, which is equal to the same value of your basic solution. So the basic solution value will be B inverse by the right hand side, while the objective function is the sum of product of your right hand side by their cost. Basically, if you want to do a minimization sensitivity analysis, all you have to is to multiply the matrix C by minus and continue with the same formulas. So let's take example. So we have a maximization of Z equals to 110x1 plus 120x2 plus 150x3, subject to these linear constraints, which all of them should have a slack variable. So when you put it in a standard form, so it's gonna be maximization of Z equal 110x1 plus 120x2 plus 150x3 plus 0s1, 0s2, 0s3, subject to 5x1 plus 3x2 plus 2x3 plus s. So you can denote it also as x4, which is equal 100, then 5x1 plus 3x3 plus s2, and you can denote it by x5 equals to 120, 1x2 plus 2x3 plus x6 or s3 is equal to 70, or your variables are more or equal to 0. So we should put it in a MATLAB manuscript. Basically, we're gonna use a linear prog command. So I have uploaded in the Blackboard this page where you can look to the linear programming problem. So basically, all the problems in optimization are minimization. So let's, for example, remember the transportation problem is The transportation problem is minimization. The assignment problem is a minimization problem. The minimum spanning tree is a minimization. The critical path method is a minimization problem. The traveling salesman problem is a minimization problem. Only come to my mind as a maximization by default is the maximum flow problem. So usually we have a minimization, and even other MATLAB codes are considered to be a minimization. So fmin_con is minimization. So basically you just need to put the coefficient in a minus value, so then you will have a maximization problem. Then all the constraints in MATLAB are less or equal. So if you have a constraint with equality or not more or equal, so you're gonna multiply it by negative, then reformulate it as less or equal. Likely if you have equality, they are put in another array, so you will have a dedicated uh, notation for equality. And also you should have the boundary condition for your problem. So this is very critical. Many students, for example, forget to put zeros for their x's, so they get unbounded solution. So you should consider that. So let's take a pick to the MATLAB code. So matrix A over here is the same one I have mentioned before. So this is your coefficient for your constraint. You don't need to put the slack and surplus coefficient. They will basically start with identity, which is saved by default in MATLAB. So basically you will just put your decision variable coefficients. Then you have the right hand side, which denoted in B. So let's go back to our problem. So this is the MATLAB code. I can take it and put it over here. Then I save it. So I make sure, for example, the first constraint was 5x1 plus 3x2 plus 2x2 less or equal to 100. So let's see the code. It was presented. So 532 with 1. Let's see the other constraint. So it was 5 plus 0 plus 3 less or equal 20. So 5, 0, 3, and 120. The third constraint was 1, 2 less or equal 70, or sorry, 0, 1, 2, 70. So 0, 1, 2, 70. Then we have the 0 for the lower bound. We have the objective function minus because it is a maximization problem. So basically this code will generate the optimal solution for your linear programming system. Well, this line here is to calculate the slack. So then run the code over here. So the problem is solved by 3 iteration. So x1 was non-basic, which have a value of 0. x2 equals to 15. x3 equals to 27.5. Because this is a maximization problem, so you're gonna multiply it by minus. So the answer is 5,925. It says exit flag 1, so you don't have any special case. In case you have alternative solution, so the alternative variable we'll consider a non-basic if you are working in the first solution. So it says 3 iteration, and we use dual simplex method. So the slacks are, so S1 is non-basic, S2 equals 37.5, so it is basic, and S3 equal to 0. So the binding constraint are S1, C1, and C3. So this is the summary of your solution. So it was an optimal with x1 equal to 0, x2 equal 15, and x3 is 27.5. So the basic variable are x2, s2, and x3, while the non-basic solution are x1, s1, and s3. So the binding constraint are c1 and c3. The non-binding constraint are c2. So let's assume that the manager wasn't satisfied with these answers. So he need more, maybe more profit, or he want to include x1 in his production, or maybe he have an extra resources, or we will add a new machine to your line. So many questions. Let's say if the your solution was robust enough to be a production plan with some type of changes. So using these equations which we have before, we can reconstruct the details for our final solution. So for example, for this matrix, you're gonna determine B inverse. So you can go back to MATLAB. So I have saved the manuscript for these equations. So basically, if you have a different problem, so you're gonna redefine, or if you are working in other iterations, so you're gonna define the right hand side. So the coefficient for your basic solution, the coefficient for or the cost for your non-basic solution, then the coefficient the technological coefficient for your basic solution, and also the technological coefficient for your non-basic solution. Usually the inverse of the matrix is very expensive, so because we are using the inverse for multiple matrix, it's better to save it in only one matrix than just recall it again. So basically these are the denotation for the 6 of your matrix, so we need to fill them. So 2 of them are filled by default by the identity and the zeros, so we don't need any calculation over here. So firstly we're gonna calculate this quartile using this matrix, so it is B inverse, but because we are calculating the whole matrix here, so we're gonna recall the NAV. So here with the matrix over here, so it is B inverse by NAV. I have put it in H1 matrix. Then we want to see if the solution is optimal over here, so we're gonna use this matrix. So this is the optimality condition check. So CV by B inverse by, again, NAV minus NCV, and we should have an array, so it saves in H2 line. Then we have the basic solution, which is B inverse by B, or the right hand side. Then we have the Z function, which is basically the solution, the cost coefficient multiplied by the right hand side. So let's run the code. So here your technical coefficient for the final matrix over here. So you fill this column, this matrix, by H1. Then we have H3 over here. So this is the right hand side solutions. Then we have H4 over here. So we have here H4. Because I have put this dot, so it will not show H2. So let's run it again without it. So H2 basically is in this line. So you can take it and put it over here. So we know X3 and X2 and S2 are the optimal. So basically we don't need to have any solutions. So the optimality condition will be 0. You can, by the way, test it, for example. So you can use the extend this formula. So AJ here will be presented in these items. So you'll pick A over here and also A2, A3, and A5 for this column. And even though, so for example, let's say someone is just picking an arbitrary solution, so if he assigned some numbers for x1, x2, and x3, he can extend both these formulas and see if he reach the optimality condition. Then he can iterate again if there is any negative in the optimality condition. So let's see which topic we're gonna cover in sensitivity analysis. So basically we're gonna see, for example, if the manager wasn't satisfied with the optimal solution and he thinks he should make some types of a product 1. So he might be thinking of changing the non-basic solution cost or profit, or maybe he's thinking the cost was very much, so that's why it wasn't in the production plan, so maybe he reduced the cost or increased the profit to put it in the line. So we'll check out the range of optimality for the objective function if it was a non-basic variable. Then we will see to what extent the solution will be the same or how much the optimal conditions are robust when we change the coefficient for the basic solution. So for example, the manager wants to reduce or increase the cost, so or increase the profits. So to what extent this will affect the production plan, because basically the optimal solution is the production plan for a factory or the case you are resolving. Basically the first and the second sensitivity topics, when we have changed them and the decision the variables are remain within the range of the optimality, so the basic solution wouldn't be affected. Any change in the other resources, basically this gonna change the whole iteration. So this is because of the effect of the shadow price. So point number 3 to 6 the solution will be changed. So we will check the range of optimality in the resources for the right hand side. So for example, inside your factory, one of your employee has injured, so you have a less hours to utilize, or you found you are out of stock of one of your resources. So to what extent this will affect your production plan. Then we will see if the change in technological coefficient. So let's say you bring a new machine and it's have a different production rate. So to what extent will change in your production plan. So then we will see it for the non-basic variable, then we'll apply it for basic variable. Then we will see the technical change if we adding a new product to your line. And finally, we'll see, for example, if you have missed of one of your constraints, let's say you just depleted the transportation, then you think it might be a constraint in your production plan. How, to what extent will affect your solution. So let's see the range of the optimality for the objective function coefficient when the variable is not one of the basic solution variables. So in our case it was x1. So basically we will grab the same formulas we have before here. So there is no any constraint for all of this, just only in this dialog. So to be remained optimal, these should be zeros, and this one should be more or equal to 0. So the least amount I'm accepting over here is to have a 0 value for any of these non-basic solutions. So if it reaches out 0, it will be start to be considered as alternative, so what we have here. Or maybe it will take one of these solution here, so it might be substitute one of the variables over here. So basically we have the original matrix which was constructed by these variables. So if you use, for example, a simplex method or one of its extension, you will end up with the same solution. Maybe you're gonna use Tora or QM for Windows. So it will become a scalar, so not one value. So C1 should be less or equal to 112. So we can change the price for C1 until it's reached 112.5. So any number less than that is acceptable. So maybe the range is between minus infinity and 112. So this is a mathematical consideration. But as engineer you cannot accept that. So you will have a like acceptable amount. So I cannot, for example, give the customer some money to have my production. So even if it's within the optimal range, so it doesn't make any sense. So we can, for example, from marketing or using break-even analysis, have more insightful range. But this is what tells you if you want to have the optimal solution without any change. So the delta over here is 2.5. If you remember when we used Excel solver sensitivity analysis, so basically it will give you 2.5, then you add it to your original, so it will give you the upper bound. So if the manager asks the production engineer to increase it by 112, would you accept the change? So no, basically because I didn't have any alteration in my production plan. So let's say the other scenario, if he asks you to increase the price to be 115. So then we're gonna check out if it's within the range of our optimality solution. So 115 basically is not within the optimality range. So we should recalculate this matrix again. So if you recalculate it using these equations again simply, so you have the same basic solution. This matrix will be not changed. This matrix will be not changed. So the only matrix will be changed is over here. So then it appear x1 right now should entering my solution. So as you see here, the calculation, so we don't need to recalculate the whole thing. We just need to calculate this dialog. So basically it tells you x1 should be entering the production. So this is gonna be your pivot column. So this is gonna be entering variable. So let's see which of the resources will be becoming the bottleneck over here. So then you will calculate theta by dividing the right hand side by the technological coefficient. So then you notice this row have the minimum theta. So this is gonna be the leaving variable. So you should do this. What does tell you? X1, if we want to produce x1, we should utilize the second row more efficient way. So this is becoming your pivot row, and the intersection will be your pivot element. So you're gonna divide it by 8.71. Then you're gonna subtract to nullify the pivot column. So there's two ways to do it. The first way is just to use the same formula over here, this formula, but you're gonna redefine C1, B inverse, AJ, and NCV, but B remain the same. So you just reconstruct this matrix again, but make sure you calculated CV, B inverse, AG, and Ni CV again. Then when you have it, you just plug in MATLAB and it will give you the matrix again. Or you just can reiterate it. So you're gonna use the Simplex method and have the solution. So right now all your decision variables are basic solution. And right now all my resources it changed to be an unbasic solution. Let's see the sensitivity analysis for the non-basic solution. Sorry, for the basic solution. So if we change the price over here, so basically we cannot manipulate this equation. The only equation we can manipulate at this time is the same equation when we used for the non-basic solution. So you cannot change the range of optimality for two variables, decision variables at the same time. So you can do only one at one a time. So let's consider C2 this time. So you will put the same equations over here the same way we have done it with C1. So we have three cases. So what is the range of the optimality for C2? Then the marketing department proposed to increase the price by 125. So let's see what will happen. The production engineer recalculated the cost and found it to be 105. So what will happen? So the range of optimality, you're gonna use this equation. So the only unknown was C2. So it will be performed over three equations. So then you will find two limited equations. Then you will see two will be bounded between these. You can use the numbering line or like any other experiment to see the range of optimality for C2. So basically he wants to change the price into 125. So 125 is within the range of optimality. So we don't have any need to change in our optimal solution, but z value will be changed. So the only variable will be changed is the state variable. So there is two ways to recalculate the right hand side, simply by multiplying the right hand side, or here the final iteration solution, by their original cost, so by 120 by 150 and adding them together, or you can use the same formula over here. So let's see, the production engineer want the cost to be 105. So we know 105 isn't within the range. So then you will recalculate and reevaluate the matrix again. So here in this time, x1 becoming a basic solution. So this is the entering and it will be leaving, then you will reiterate again.